So welcome everyone to this very exciting talk on reinforcement learning for RoboRacer. And so RoboRacer, formerly known as F110s, is a autonomous racing with scaled vehicles. And this has been deployed over 90 universities worldwide. And through many competitions that we've held, over 24 in the past 5 years, 24 international competitions, we've had a lot of teams actually become super elite teams in racing. And today it's our great pleasure to have Eduardo Linon from ETH Zurich and his team. Actually, it's not just him alone, it's his whole team of ForzaETH who have developed over the years a series of improvements on their perception planning control pipeline for autonomous racing. And Eduardo is going to tell us his story of how he has developed this over the years. And we are very excited to see what you have to say. So welcome, Eduardo. We are very excited to hear your talk.
Thank you, Rahul. So let me start. As Rahul said, thank you again for the very kind words. This will be a bit of a story on reinforcement learning for racing. This will be a little bit of a ForzaETH story. By jumping on the first slide, this will not be only a story about myself, but this is also a story on the ForzaETH student team. First, I can as well start from myself. I am a PhD student at the Center for Project-Based Learning at ETH Zurich. And I'm working mostly, let's say, on learning-based controller on physical platforms. The main physical platform I've used until now was the F110 car, now RoboRacer. And I really started my PhD. I remember one of the first tasks we had was watching the live stream of the 2021 IROS competition, I believe. And I started that time. I was only a master degree student, as many of you might be now in the room. This was October 2021. But after that, soon in February 2022, we found the route of what is now the ForzaETH autonomous racing team. As already Rahul anticipated, we took part in many of those competitions. The first one was ICRA 22, where the competition was also held in parallel with the Opportunities and Challenges with Autonomous Racing workshop, which will come in later too. And there we got 4th place. Then we iterated, we improved our algorithms, more info on that later. And then later the same year, we got our first win at the Germany Grand Prix. I believe it is named on the official website. And then we improved the team, we got some new members, and then we got again another win in 2023 at ICRA. We had a bit of a pause from races, and then we went again at races in 2024, where we had somewhat of an FTG debacle, because as I saw, also there is somebody from Vol in the audience on Zoom. Their Vol had a very, very fast car, and it was more or less, let's say, based on a very simple algorithms. And this hurt us very, very much, because it meant that we had a bit of a slump after the win, especially, and that meant we had to work more. However, we tried to work more, and we came again at IROS same year. We had some problems. We have maybe some strategic missteps. We were trying very hard reinforcement learning too at that IROS. It didn't work. We ended up 3rd place. And again, we tried once more with reinforcement learning. This was Milan 2024, very, very recent. It was in December. But our car crashed quite hard during like half an hour / 1 hour before time trials. And that went bad in the end with an eventual 4th place. Now we're preparing for ICRA 2025. And in the meanwhile, what happened to the team really is that we became an official student team. We have these three main pillars. One is education and outreach, just with, for the moment, local companies and associations. We are bringing around STEM information. But the other two pillars, research and racing, are those that I will delve a little bit more into today. Research will be the different projects that pushed on the development on our F110 car, and racing. I mean, racing in the end is the main goal of this F110/RoboRacer community. So to start, okay, that's a little bit of a schedule. First, to state from a baseline, the foundation of racing of ForzaETH. I will go more into the foundation of racing from the control point of view. Of course, a little bit of a disclaimer, we have the full ForzaETH autonomous race stack. It's open source on GitHub, you can all go and use it, but we'll focus a little bit more on control and classical control for the first part. But then we'll go more in depth into the RL part, RL for racing, as I've heard many of you are also interested from the audience in UPenn to develop a project for the course. And then there is a bit of a conclusion, takeaway messages, etc. Now, going into the baseline, there is a little bit of this difference between controllers, right? I believe many of you know already. There are reactive controllers that just process input data that can be sensor data, LiDAR, 2D LiDAR in the case of F110, and gets you an output, directly steering and speed. These can be very fast. This can be also very simple to develop, right? It's the first in I've seen in your syllabus is the first controller. In what we do at ETH is also the first controller that everybody develops. It can be very simple, can be very performant if you optimize it very well. However, it doesn't really rely on a racing line. Also, it's kind of really reactive, and it's not based on a racing track. So one first thing that people can do is to take the ego pose, so a state estimate of the car, take a race line, and then create from there an output. These are roughly called the geometric controllers. Pure Pursuit is one example of them. And then if you want to go even more complex, you can take into your controller an extra model, which gives you a lot of other issues in complexity, but can give you a lot of performance. And here we are talking, for example, about MPC. Now, if you take one of the main controllers that people use at the beginning, Pure Pursuit, there are different pros, like it can track a trajectory very well, which is very nice. It's very simple because it separates lateral and longitudinal control, meaning that you can focus in a separate way to try to follow your velocity profile. You can even optimize your velocity profile in a more or less separate way from how you optimize your steering, which in Pure Pursuit comes in this somewhat of a simple way based on the look ahead point. Now, however, this is a non-optimal control technique, differently from MPC, but it's based on very simple kinematic assumption. So if we go back basically to how Pure Pursuit works, I believe many of you have already seen a slide like this or similar. Pure Pursuit is basically hinging on the assumption that the front wheel does not slide. I mean, both wheels do not slide, but the front wheel just goes straight on the path that's dictated by the steering angle delta over here. And then you measure the instant curvature, radius of curvature, which you have the same angle delta by just trigonometric relationship. And then you can get your steering angle in a very, very simple way once you are given this radius r and the length of your wheelbase LWB. Then the steering radius r can be obtained by the look ahead point. Now, this of course has very, very strong assumption, the strong assumption of no slip. You assume your front wheel to just go straight. And this was the first, let's say, issue that pushed forward our ForzaETH team, because this is where we developed our first main controller. So we are talking about the model and acceleration-based pursuit controller, or MAP controller for short. And as you can see, MAP works very similarly to pure pursuit in the first part, where you take a look-ahead point over here along the race line, you compute a radius of curvature, and then by very simple assumption on how the car is having a constant radius and constant velocity turn, you get your lateral acceleration. Now, this lateral acceleration is then passed together with the longitudinal velocity that you want to get to a lookup table. This lookup table is generated by steady state simulations of the car model and is used to give you a steering angle delta. Now, the steering angle delta will be, of course, coming from a lookup table that is steady state, but since you repeat anyway the process in closed loop, this will be very fine. And actually, this was very, very fine because on one side, the whole MAP paper and the publication at ICRA 2023, and together with that, we also managed to get the first place at the F110 competition at the same conference. Now, this is a very old video. This is actually one of the oldest video of MAP. And as you can see, this is actually a replica of the ICRA 2022 racetrack. And this video is also one of the first and fastest recordings we had at the moment, because this is one of the first time the car was going over 10 meters per second. As you can see, MAP is able to drive at this speed. Actually, 10 meters per second are reached on the far part of the track, so you can't really see that part really well. But MAP can give you very nice results, can incorporate a little bit of model in a very simple controller, which still doesn't have the complexity of MPC. But in general, it still needs a model, right? And obtaining a model can be hard, because especially MAP specifically needs just a Pacheco tire model. But to obtain a Pacheco tire model, usually you need to run steady state experiments. Those steady state experiments basically consist of just driving in a circle at very different constant velocities and very different steering angles. This requires, of course, a lot of space, and not always the space is available. So what's perfect? Like, this is an example of such a steady state maneuver. And I mean, as I said, the model needs system identification, and system identification needs large space maneuvers. However, this is not always available. And this is where, from this need, the second step in our research path came into life, which is learning based on track system identification for scaled autonomous racing in under a minute. For short, it's on-track SysID, which was also published at the IEEE Robotics and Automation Letters. What does this consist of? There is a big scheme over here, but the main part, everything starts from on-track real-world driving. So you don't need anymore the space that was needed before. You just drive on the track, the same track that, for example, you are using at your competition. And then from this data, you have a nominal vehicle model. Using this nominal vehicle model together with, let's see if I can get a pen. No. Using this nominal vehicle model together with the data, we train a neural network to learn errors on the lateral velocity and the yaw rate dynamics. And then we obtain a corrected model, the nominal model, which is a dynamic single track Pacheco model, and then a neural network that gives you update. From this model, we can then simulate the Pacheco parameter identification, those experiments that I showed you before in this video, which, I mean, I will not run again. And then we can obtain some new updated Pacheco tire parameters. We actually, this path for a single set of training data, this upper iteration is run multiple times, 6 to be precise right now. And it's been shown empirically that this can leads to convergence of tire parameters, and for what you can measure on the F110 actually leads to the same quality or even better sometimes, same quality parameters as steady state system identification, but it removes you the need of, well, a very large space, which is not always available. In the end, after you have the new type parameter, you can update your lookup table, you update your MAP controller, you can update your MPC controller too, and then you can race against and race fast. Here we have a little example of how the model is working. And as you can see, in under 30 seconds of data acquisition, you have new data that can be used. In this specific video, it's only about showing 2 iterations, but you see that from real data, you can get novel tire parameters. And in this way, you can really improve your tire model. Now, from these 2 parts, we get this really strong baseline. And I would say that on the control side, up until now, more or less, this has been one of the fastest controllers that we have. If you take only traditional controllers, of course. On one side, we have the high performance baseline, which is MAP, which can go very fast. On the other side, we have the very versatile and easy to run system identification. Now, what about reinforcement learning though? Because we also have a lot of, a little bit, and let's say a long time experience on reinforcement learning. I think one of the main starting points for reinforcement learning in racing was outracing champion Gran Turismo drivers with deep reinforcement learning. I mean, it's just these Sony AI papers that showed that with reinforcement learning, you can reach very high performance head-to-head driving behavior that can beat even the best drivers. Here we have a little bit, a couple of lap times, and you can see on 3 different tracks, we have 3 different drivers that achieve the best lap time, and all the lap times are slower than the best performing Gran Turismo Sophie. It's the name of the agent, of the reinforcement learning agent driver. The RL agent was in the end faster for all the 3 circumstances. Also, there was kind of a big event of a race where in the end, after a rematch, the Gran Turismo agent won with no doubt. Now, part of these results were also presented at the opportunity and challenges on autonomous racing workshop. And actually, a funny anecdote, at that same workshop, we also had a paper. This was called TC Driver, a trajectory conditioned reinforcement learning approach to zero-shot autonomous racing. And this was our first foray into the world of reinforcement learning for F110. And well, at that time, the best results, the main results were in simulation, where we showed basically that enhancing the reinforcement learning controller with an observation that specifically had to also include a trajectory from an expert driver. In this case, in simulation, it was an MPCC expert driver. We can see that this improves a lot the generalization of the reinforcement learning agent. Here on the right, you are specifically seeing an evaluation on a track for which the agent was not trained. So the agent was trained on actually a very small track, still with a varied type of corners. And you can see that already by smartly designing the observation space and training, you can achieve much better generalization than an end-to-end compared agent. As you can see, all the crosses here represents crashes. The first two tracks, we have even 0 crashes for 200 randomized runs of the TC driver, which is this trajectory condition driver. And in the last track, we have many fewer for TC driver than for the end-to-end baseline comparison. And if you can see, this is a table actually on a little bit of a different experiment that didn't fit really in this slide. If you change the parameters to something very outside of the training range, let's say specifically for end-to-end and the TC driver, you see that still maintaining this type of extended observation space can help a lot, well, to reduce the crashes, to increase the average advancement on the track, and also to increase a little bit in lap time. Now, the MPC for comparison here is a little bit weak with a lot of crashes, but the MPC is a little bit as a disadvantage for this specific comparison. However, these results are mostly in simulation. The real meat in F110 comes with the real platform, and the TC driver at the time was nice also because it could drive. It could drive on the real platform with 0 fine tuning. It was basically 0 shot transferring the behavior from simulation to reality, but there was still a clear mismatch due to the sim to real gap. The car was much slower, well, was kept much slower, but still the whole feedback loop was inducing a lot of oscillations, as you can see, and still it was not a performing algorithm from a racing point of view. From there, we thought, what can we do to improve the performance of the algorithm just by training in simulation? And well, what we did was, it's called RLPP. It's a residual method for 0-shot real-world autonomous racing on scaled platforms, and this was also submitted last summer and now will be presented at this ICRA. But RLPP basically builds on this paradigm of residual controllers, where, well, RLPP stands for RL and PP for pure pursuit, where you start from a baseline controller, which is a pure pursuit controller, you add a reinforcement learning agent that is trained, and in this case is trained in simulation, and then you deploy it on the real platform. Now, keeping this structure can leave you a little bit of tuning capacity, and with tuning is not really fine tuning on the real platform, is still tuning in the amount of reinforcement learning that you want to give to the pure pursuit agent. And by tuning this weights, basically, you can see that RLPP exploiting this structure can improve on the baseline controller on which it is, even on the real platform. So these are all numbers on the real platform, and pure pursuit, as you can see here, starts from around 14.35 for a lap time, and RLPP manages to improve it by quite an amount, around almost 1 second. Now, RLPP still doesn't manage to achieve the top level performance of MAP or MPC, but it kind of quite closes the gap by using the F110 simulator, and can also overcome the previous limitations of TC driver. However, a sim to real gap still exists, and it's still quite holding back the performance of reinforcement learning at this time. Now, when you then are facing this type of problem, you're somehow a dramatic crossroad for reinforcement learning. Either you want to improve your simulation, or you want to move and you want to go training in reality. So a little bit of the first part, simulation learning dynamics. This can sound very interesting because it was studied a lot on a different platform, the robot quadruped, And as you can see, there are two main points that are made to build this structure. One of them is really learning your model. In this specific example, learning your actuators. The animal quadruped has elastic actuators, which are very hard to model with basic kinematic or dynamic formulas, and therefore are much more easily modeled by neural networks. And on the other side, this is also enabled by massive parallel deep reinforcement learning. Well, these two steps, while they have not specifically been replaced in F110, they are part of our work, and they are actually part of a work in progress. And as you can see, something very similar to what was before residual error model learning is being made for an F110 model, and this is very well is part SysID from before. And from another side, this is of course a work again not from us. On the right, you can see this F110 simulator from the University of Washington this time that extended the Isaac Lab environment, which is in the end the same environment used for quadruped robodogs, also to small-scale autonomous racing. And now this is a work in progress, but we actually have a reinforcement learning agent that's much faster. And to develop that, we went on a totally, let's say, parallel direction, which is training on the physical robot. Again, if you want to start, well, if you want to start from previous state of the art, we see again a robodog, and in this case we see Daydreamer, world models for physical robot learning, where they are specifically trying to use the Dreamer model, which is a model-based reinforcement learning approach, to train on the real robot. As you can see, it's still weird in the first half of the video, but in the end, it manages to learn, right? So again, of course, this is not work from our lab, but it's a previous work that shows the feasibility, in this case 30 minutes, of training reinforcement learning on real robots with no specific constraint on the real behavior. I mean, the robot will still learn, but you can see at the end the behavior is still reasonably robust. And even though this video they're making the robot flip fully, the dog is still moving. Now, what does this mean for the F110 platform? Well, enters what we kind of call internally Schumacher-L, which is our reinforcement learning agent trained on the robot. This is actually work it's currently under review, therefore it's still not open. But we basically replicated the training on the real robot with many different algorithm differences, of course, from what is previous state of the art, and many of those differences were, of course, needed for making it work on the F110 car. And specifically, as you can maybe hint, if you can maybe guess from this depiction, everything is run on board of the actual robot. Both the training and the acting are run on board of the Intel NUC, and the structure, similarly from before, is built on top of a base controller, which will be MAP in this case, and a neural network, which will be our reinforcement learning agent. Now, to go a little bit into the, let's say, results of this robot, we can see that specifically on these different tracks where we evaluated the training and deployment, this specific algorithm, in this case, when we merge reinforcement learning with MAP, we call it RL-MAP, achieves the fastest lap time of all the algorithms. You can see on the first track as the fastest lap, on the second track, where we had slightly more slippery tires, again, it manages to beat MAP, this time for a little bit less of a gap. And again, on another evaluation track, once more achieves the fastest lap time. And it's this structure where you pair a traditional controller to a reinforcement learning policy was tested against different baselines that we had in our we have developed in the race stack. And in all the cases, you can see here with MAP, here with Pure Pursuit, and here with FTG, the reinforcement learning agent manages to outscore, respectively, the performance of the baseline controller. So here the dashed blue line is the baseline controller, and in all these three cases, it manages to outperform. Now, maybe you are wondering why there's no MPC or RL-MPC fusion in these two methods. And the fact is that RL and MPC work a little bit worse, especially in this residual control structure, given by the clear pre-planning that that MPC does at every time step. Specifically, when you try to push the car with reinforcement learning, a simple controller such as MAP, Pure Pursuit, or even Follow the Gap will not particularly try to counteract hard the RL input, especially when the RL will try to cut corners or try to basically push the accelerator more than normal. However, when you try to merge RL with MPC, MPC will have its set of constraints, its model, and if RL will start push harder, MPC will try to brake harder, and these counteracting actions really break the whole setup in this specific case, and therefore the fusion of RL and MPC was not studied anymore in this specific framework. There are different ways RL MPC can be put together in also a racing setup, but in this case it didn't really work. On the right, then here you can see that the pure RL agent, when it's compared with the same training time of the other algorithms, doesn't reach the performance of the dashed line. Here the dashed line represents our best baseline controller, MAP, and this dashed line really still far from RL in this specific circumstance. Now, when we want to see the performance of the first comparison, here we have RL MAP against the end-to-end reinforcement learning approach against the MAP, and RL MAP is, in this specific case, the fastest. And here we have 2 laps of the whole approach. And you can see that it's really faster at quite a significant, with quite a significant margin.
Eduardo, I
the end-to-end, yep.
We can just take a pause and just see if there are any questions. So people in the room, people online, if you have any questions.
I have a question.
Yes, go ahead.
Yeah.
On the last slide, 26, RL for racing, training on the robot, every method like Pure Pursuit, Follow the Gap, Pure RL starts with times slower than the baseline at the beginning of the training. And the RL map is the only one that starts faster at the beginning of the training. So the not initialized network is already faster, like with MAP.
Yep. So there is a couple of points on these plots. meaning one of them is that the non-completed laps are not shown. So I guess what is happening in this specific plot, we are just plotting one of the trainings in this one, and what's happening is that at the beginning the controller is not managing to complete any lap, right? So MAP is somehow pushing quite hard. The RL is trying to go even faster, and therefore we don't get any completed laps, but still we get, I mean, meaningful samples, right? We get rollouts, partial rollouts of a lap, and then after that the RLMAP starts already learning at a quite fast, with quite a fast lap time. I believe this
All right.
is.
Thank you.
This lap. You're welcome.
Any questions here?
So
you can
if I
just
under-
come up. You can just
Okay.
come up.
I mean, maybe you can just repeat the question. Like since it's online RL, right? So do you have to reset quite a lot during the training process?
So it's online.
So
So do you have to reset a lot during the training
Yeah.
process?
yes, yes. Specifically, I mean, the episode needs to get reset very often, and actually, I have a second. Put this again full screen. I have an excerpt of the training run on the next slide, I believe. Yes. So this is the end-to-end RL training, and as you can see, there is a safety filter, which is a very simple safety filter. There are more details later, but the safety filter basically resets the environment. The reset is made so that the car starts again to drive with the baseline controller. So the reset is fully automatic, and the car gets back on track autonomously, and then when it's back on track, it resets learning. So yes, there are a lot of resets, but they're more or less automatic from a procedural point of view.
If there are any other questions online, please go ahead and ask.
I have a question. In all cases, for all controllers, they're
Yep.
reference tracking controllers, right?
Yep.
So the performance of all of these controllers depends on the reference that you're tracking as well.
Yep.
So I'm curious what the reference you use and how do you calculate that for each of these controllers? And
Yep.
does the reference change after the training process, let's say, based on the performance of the controller or something similar?
Yeah, no, that's a very good question. The reference is the same for MAP and the Pure Pursuit controller in the comparison, which is the minimum curvature race line, which we use across the race stack for mostly all of our racing strategies. This minimum curvature race line, I mean, it's an adaptation of the TU Munich Global Raceline Optimizer, which I believe is one of the most sponsored, or let's say used, raceline optimization packages in F1 10th, and of course is an optimization in which we did a little bit of tuning on how to generate the end trajectory, but it's in the end a minimum curvature raceline. To the second part of the question, I mean, the first part is the same for MAP and Pure Pursuit. Of course, it's not the same for Follow the Gap. Follow the Gap is just based, in this case, purely on the LiDAR scans. It doesn't change after the reinforcement learning training. But what could be very interesting, which is an idea that lingers around, is it could change. Specifically, we could take the reinforcement learning lap, either multiple laps or the fastest laps, and we could use those to update our race line. In this case, we could use this updated race line either with MAP with pure pursuit or even with an MPC controller in order to have actual safety constraints on the boundary, and that would likely be faster than the normal controllers and the normal race lines.
I see. Thank you.
Well, and just a follow on to that, how would this
Yep.
now extend when you have dynamic opponents?
So, well, reinforcement learning for dynamic opponents is, first is in this specific video, let's say in the specific agent displayed here is not there. There's no overtaking capacities. It could extend, being it a residual controller, you could still deploy it, but since you have no observation of the opponent, it simply doesn't work, right? I mean, it's not supposed to work well enough. However, we are with multiple projects in the background trying to develop something also for opponent overtaking. We're quite hopeful for those results, but yeah, I mean, basically it would consist of the first two simpler or foundational step of including the opponent observation, at least for one opponent at a time, especially given the current structure of the competition, and then modifying the reward in order to enable the agent to optimize an expected return that also takes into account the overtake. So yes, basically, it's a work in progress.
Of course. All right. Thank you. We can continue.
So we continue from this example of training on the robot, which, I mean, as you can see, as you saw also before while I was talking, there is a safety filter that gets activated many times. The car gets automatically get back on track. And then here specifically, you're seeing the end-to-end controller, which, well, it's starting very slow. But then after a wall time of around 22 minutes, I don't remember specifically when, it does get, first it gets the same wall time as the other controllers, and it has this type of lap, which still is very tentative in some corners. It seems like it doesn't even want to negotiate the corner because of, scared of crashing. But it completes an entire lap without needing safety filters or resets. Now, we'll see later, I believe it's later on a different slide, that anyway, if you train the end-to-end controller for more, you can get a little bit of a better performance. However, there are different points in this original structure of, let's say, the Schumacher that made it possible. One of them was this strategy of training and active both on the same platform. Now, this is based on the algorithm, and to really have a little bit a better grasp of how the algorithm enables this specific training, we'll just have to quickly have a difference with what was used before, in especially the related work cited before from, of course, this is a different lab at ETH, but working on the robot dog, they make use of massively parallel simulation. And most importantly, in this comparison, they were using PPO, which is a non-policy reinforcement learning algorithm, meaning that the policy that you want to deploy needs to be acting at every sample time, at every sample that you take from your environment. Therefore, it requires a lot of these samples on policy have a massively parallel simulation. And usually what you get from on-policy algorithms is that you can do very, very fast training. However, with F110 or RoboRacer, or in general with autonomous racing setups, you either don't have specifically, well, you just don't have the infrastructure specifically on Isaac Lab, or if you want to drive on a physical car, you just have a limited numbers of car, or even one car if you don't have the infrastructure again to drive to run parallel simulation. Therefore, what you want to do instead of the previous work is to work with off-policy reinforcement learning algorithms. These algorithms do not necessitate the agent to be on the car to be exactly the same as the one that's getting samples in the environment, and therefore can enable this crucial structure that was used in our system for learning on the car. What was really needed, this structure is composed of an acting agent, or this reinforcement learning controller, which runs at 10 hertz on the car, which is completely separate from a training node, which just receives the samples from the car driving around the track and then runs the whole part of training as a replay buffer. It fills up the replay buffer and then updates the samples. It gets new policies. These new policies have updated behavior. These policies are synced on the acting agent. This process is run at 1 hertz specifically, and in this way we managed to get an off-policy RL algorithm, which is notably, it is more sample efficient, but it lacks a little bit in the actual training time. However, this enables to actually train on a real platform. And this was one of the crucial adaptation that were needed to SAC for enabling reinforcement learning directly and fully on the real car. Now, another part, this was what I was referring to before, is that the task is much simpler. I mean, this is more or less a little bit of a given when you compare the end-to-end task versus the residual controller task, where you have already a baseline controller and then you have to drive only a residual, or let's say even an error control strategy. And when you train these two types of controller for the same times, you get what you expect. The end-to-end training controller is slower. However, when you train them for reaching the same performance, I mean, not however, but similarly, when you train them to reach the same performance, the end-to-end agent in the end ends up needing 3 times more wall time to reach a similar performance. Here we have the specific numbers. As you can see, the best performing RL MAP has a minimum time of 926 and a mean time of 956, and the end-to-end RL trained for longer, unfortunately there is not the marking, but the second line here is the one trained for longer, reaches a similar minimum time, not the same, but a very similar minimum time and average time. And this specifically was trained for 3 times longer. Here we have a histogram with the same data. We have the MAP. This is the baseline MAP lap time, and here we have the end-to-end controller, which was run basically for 3 times. So really, we see not only that a simple task is simpler, but the residual controller is needed to achieve training in the 20-minute time slot that we prefaced. And this 20-minute time slot actually has a meaning. It's not a fixed 20-minute time slot. It's actually given a fully charged battery is the lifetime of one battery. Now there is a final step on which is really a key part key component of this RL algorithm, which was also already noted by the questions before, which is the car still needs a lot of resets. The car needs to learn, especially at the beginning, of course. It will try to push hard, and well, it will end up in the wall. And what was implemented for this specific RL algorithm was a yaw-based safety filter, which automatically kills or automatically ends an episode whenever the attitude of the car is particularly different from the race line. Now the details are not on the slide, but what actually one might argue is that okay, but then you are really forcing the car to be aligned with the race line. Yes, and to avoid this extra constraint, which might be limiting the performance, given the fact that we still want the reinforcement learning agent to have freedom to not be aligned with the race line, the yaw-based safety filter actually is implemented with a curriculum strategy. This curriculum strategy basically constrains the yaw more strictly at the beginning, and then every time your behavior improves, which means in this case, in this specific case, it was every time you complete 3 laps, if I'm not wrong, the yaw constraints get wider and wider. And at a certain point, the yaw constraint is just completely deactivated, or equivalently, I mean, it's set to 90 degrees, which is at a certain point is definitely something that you do not want your car to be. It's a yaw state in which you don't want your car. Now into some more general, onto some more general safety filtering. You can see that this is quite a simple strategies, and indeed there are nicer ways of implementing safety filters, also for racing. This is again another related work from another lab, this time still at ETH, but not from us. And you can see that this car, even without inputs, can drive around the track. And then an imitation learning policy is further shown, and the imitation learning policy is unsafe, but the filter is really trying to keep the car on track. This filter is based on an MPC, is, well, in the family of MPC safety filter, and in a really much more general way, tries to take the desired control signals, tries to see if these desired control signals would steer the car into a wall, if you want to put it very, very simply, and then modifies in a minimally invasive way this input in order to keep the system within the defined constraints. This work was also in another paper. Again, this is related work from another lab, was tested actually together with a reinforcement learning agent. And the problem that you get when you try to do safety filters plus the reinforcement learning agent is that when you do reinforcement learning, you want to crash. And when you use a safety filter, the safety filter will avoid crashes, basically. So you have to tackle this interaction between the safety filter and the reinforcement learning agent. And here you can see we still have the same safe environment as defined in the previous diagrams. And what you see that is really crucial is that you have to correct your reward, because when you crash, or in this case when you do not crash, maybe you want to count it the same way as a crash. So I mean, this paper, again, not from us, is really recent, January 25, but it basically highlights the fact that reinforcement learning and MPC safety filters are really an interesting, two interesting algorithms that can be used together. And indeed, we are working on and to merging the two, and also trying to have the a safety filter RL racing driver for the F110 Plus. The basic, let's say the basic safety filter setup with a safety filter in a reinforcement learning algorithm, in a high performance racing algorithm, what we can see is that sometimes, given the fact that we want the highest of the performance, we might be at the constraint boundary. And when you are at the constraint boundary, what happens is that the modeling gaps become really exacerbated, and they will provide really excessive conservativity. This means that if we want to already deal with these preliminary results, what we are seeing this time, these are from one of our students, from Diego specifically. You can see that we have the MAP controller in blue, which only reaches a certain amount of multiplier on the race line. And you see when you apply the safety filter, you get a little bit, what is clear at lower multiplier is that you get a bit of more variance. And then at a certain point, you will get a really, at the edge of performance, you get somehow of a much worse average, which really is a little bit of a problem when you want to interconnect safety filter, reinforcement learning, and, well, high performance in this case. And especially if you will be driving a reinforcement learning agent, this will try to push the performance much more. And in the end, this is why this whole setup is indeed a work in progress. Now, if this part was, let's say, one of the latest sources of a work in progress, and we can start more being into the end of the general talk, which is about the main takeaway messages that basically we say we got while trying to train reinforcement learning agents. I guess one quick part that I can give before going to the, let's say, conclusion part is if there is any more questions on the parts before, maybe this could be the time. Any
questions
question?
online or in person?
Yeah, I have a question.
Yep.
I know that you guys have more than one car, so I'm
Yep.
curious if how well do these agents generalize between more than one car? I'm assuming you're training on one car and testing on one car currently, right?
I mean, we're training and testing on the same car.
Mhm.
For when we want to test specifically for generalization, we try to change, we change the tires of the car.
那就5月吃饭呗，5月过完
And
5月后跟曹博吃饭呗。
specifically for well, for generalization, this specific agent that was shown before, well, let's say it's still this agent, doesn't generalize well. Doesn't generalize well to the different tires. We never really tried too much on different cars. I believe well, we have cars that are more similar to others, and I believe to a certain extent it could generalize, but still it would be somewhat hard. And yes, for this reason, I would say generalization is still very hard. It's still a work in progress, and we have a little bit of a better result with if we run a little bit of fine tuning, still with that agent. But yeah, those numbers are not currently in this slide deck.
I see. Thank you.
Welcome.
Hi, I have a question.
Hello.
Thank you
Yep.
for the presentation. So as a percentage, what do you think the performance gain from RL is from first, model matching? Second is the planning, where you see you have a value function where you have an active replan whenever you're on the track. How much percentage do you think? Is it mostly from having a more accurate dynamic model, or do you think it's getting a higher performance trajectory? I mean, it's not trajectory, but it's more like a value function that's being tracked.
So that's a very interesting question. Well, if we consider the models that before were trained only in simulation, right? I don't remember if I have. I mean, I have a slide at a certain point on those. For sure, the improvement over here is when you go from pure pursuit, or when you go from TC driver, RLPP, to the other controller, let's say Schumacher L, which is not in this table because this table is from RLPP, to Schumacher L, which you can more or less compare into the MAP. At the MAP performance, maybe it's a little bit better, but comparatively still quite better. But you can say that at least all this gap is given by the model mismatch, right? Because those are trained only in simulation, and the simulation is inaccurate compared, of course, to the real world. Then when you go into the final, let's say the on-car algorithm, here, I mean, there is, of course, a whole part at the beginning of learning the value function, which, well, it's not pre-trained or anything. So the initial part all still needs to learn, and then when you see at the end of the learning phase, let's say of these first 20 minutes, once I believe you have quite a good value function, you start to have improvements due really to exploration in around a very performant RL raceline or very performant value function. I would say at the moment from this result, it's, well, much more marginal to the results of just, well, training on the car.
Yeah, I see. Thank you. Okay. This is a quite a significant performance increase from NPC, which is also also having your system ID'd model, right?
Yeah. I'm not sure it's stable, but yes, it's quite significant. I mean, yeah. Sometimes performance with MAP comes because, yeah, MAP just follows the velocity controls, and MPC also because of some possible model mismatch is overly conservative.
I see. So for I have another question. For the do you put LiDAR into your input, or is just state?
So I have, I believe, something that could help a little bit. Yeah, of course, this one. Okay, so as you can see here, okay, this might be, I believe, a little bit misleading because there are rays from the LiDAR to the track boundaries, and then you have this observation track. What is actually this observation track is discretized points along the race boundaries as from your state estimation and the whole global plan that you have. So at least you're not subject to well, noise on the LiDAR. or for example, the LiDAR seeing the ground or reflections. But that's like, I mean, this is just an alternative that that works, but you really need, well, for example, you really need boundaries, not only virtual boundaries. And as you can see in the videos, we train a lot with virtual boundaries. And in this case, LiDAR observation would really be useless.
Yeah, okay.
We
I
could
see.
do virtual LiDAR, but
Yeah.
at that point, it's the same as.
But for the RL problems, you have a pose on the global map, or you don't take that as an input?
Sorry? I missed part of
Yeah,
it.
the localization that's on the global map. I think that's what
Yeah.
Robo means.
Yeah, no. We had at the beginning because, well, that was helping a little bit, right? But now we don't have any more. The observation is not. The observation tries to be as general as possible to incentivize generalization. We really have only a local view on the map, so the next points on the track, and then states of the car, longitudinal velocity, steering angle, the last input, lateral velocity, and yaw rate. Yeah, the observation of the track needs mapping because you still can see behind corners, but yeah, we don't
You
have
do
like
not have
global
like you
state.
do not have like an
No.
explicit race line optimization.
We also don't have we have. This is the same a priori race optimization that that were also discussed in the question with Ahmad before. The same minimum curvature race line that's given at the beginning for MEP, Pure Pursuit, and also Schumacher.
We have one more question here.
Yep.
Well, thank you for the talk. I was wondering, so like for your training on the robot, how long does that usually take? Like, what is sort of the sample efficiency? Because you can't really do, I guess, parallel simulations in the real world when you're training in the real world.
Yeah. So usually what we saw is that in 10 minutes the car starts to be driving, and after 10 minutes you really start to push a little bit of performance. Maybe these plots might be a little bit on the nicer side, but still you need approximately 10 minutes of sampling. Now, this is we carried out all the evaluations in wall time for this paper. I am not 100% sure what the numbers in specific samples are for these examples, but I mean, at an the state estimator and data gatherer works, I believe, at 40 hertz or 50. So that's 10 minutes of state plus a little bit of skips in between. That's maybe 66, maybe up to 50,000 samples. The car starts to maybe drive, maybe from 100,000. Maybe my calculation are a bit wrong. The car starts to drive quite well.
Thank you.
Thanks.
Yeah, I have a question.
Yep.
So if we consider boundary constraints, what are the challenges that we will face? Because right now we are not considering them.
Because there are actually different issues with boundary constraints, right? One of them that we faced is that sometimes crashes are not detected. Or in general, do you mean, do you want actual constraints in the algorithm?
Yeah, I mean, right now what track you're considering, I guess it's hard to parameterize the boundary constraint. But if we change the track and the boundaries are like parameterized. We have the somewhat nice curves. Can we embed them in algorithm and say, okay, these are my constraints. Now plan between the boundary.
Yeah, I mean the boundary are still in the currently in the input of the car. There are some extra results, again, are not here, but the car, to a certain extent, has some generalization properties to different tracks. It doesn't drive as fast as the track on which it's trained. It can drive quite fast if you do a little bit of fine tuning, but still the track boundaries relative to the car's position, they are in the observation of the agent.
I see. So it's not just the tracking path that we consider. The boundaries are known, and so it knows
the boundaries
I can take a certain drift over the curve or something.
Yeah.
Okay. Thank you.
Yeah. We know also the relative, like the boundaries are input with a relative coordinate to the car. So we also know our position with respect to the boundaries.
Okay. Interesting. Thank you.
Welcome.
Cool. We can continue.
Okay, perfect. Then safety filter was actually the last part before the latest part of what I wanted to go into, which are a couple of main takeaway messages. As I've been told, many of you are actually preparing a final project on reinforcement learning, and maybe also want to join the race in the future with reinforcement learning. And I would say that the first, one of the first very important takeaway message that I would give out is just always do metrics, always do plots. First example, of course, it's racing. So the main metric that you should always look at is lap time, and very possibly you should always look at the same track so that you know when your algorithms are actually making improvements. This might sound simple, but it's sometimes it's quite hard to transfer behavior across different tracks. You never know if it's because of the track configuration of anything. So maybe having a fixed track is a nice idea. And then, of course, metrics and plots or visualizations goes much beyond just plotting lap time. Of course, you can plot your distance to the boundaries. You can plot, of course, your trajectories. This is very important. And then you can start going more into depth. This is another plot from one of our student. In this specific case on the right, it's Joel. This is the average gradient of action with respect to the input feature. This is another plot that's very important because you can see how the different input parts are acting on the final state. And you can see with this what is having the most effect on your output. You can better shape your input. You can better save some computation in the neural network structure, etc. And then another very important evaluation is to see that, especially when you do models, that your model is correct. Again, this plot is from another student. I believe the student might even be in the Zoom chat right now. This is from Luca, and these are trajectory numbers from the lab. And one of the things, the main takeaway message, that if you don't have metrics sometimes, and if you don't have a lot of metrics, sometimes it's really hard to evaluate if your models, if one model is better than the other. One of the other thing that also Luca did was, well, evaluating a simulation score and then assessing many other metrics that are really important to keep track across your progress on whatever you are doing on different things. And again, another plot. This again is from Joel. Again, same plot as the one right below. Very important when you do reinforcement learning to, well, check out the total reward. Together with the total reward, of course, check out your lap time, because Usually it's hard to minimize directly lap time with a single reward. It's a little bit too sparse. So you want a proxy, and then you add other regularizing rewards, such as you minimize Y velocity. Maybe you can't see the label, but this is Y velocity. Maybe you have the relative heading filter. This is specifically the one we were talking before about the yaw. And you want to see how the different runs, how the different rewards act together, not only the general reward. And this is quite important to understand what's happening with your reinforcement learning runs. Now, another point that's really clear is that you want to close the real to sim gap first before the sim to real. Two examples, I mean, this is from the literature. So these really animal, they learn actuator models. This is from us. I mean, we close the real to sim gap by completely removing it. And this is very important. There's also very recent publications, I believe. We even have Gregor in the audience right now. This paper, which is really one of a very hot paper now because it's out from 2 weeks, 3 weeks, highlights and underscore the fact that you have to close your real to sim gap first. They highlight again, actuators need to be modeled very well. Your simulator must be very nice. And I mean, this is another work, this time very recent, with RL racing policy on the F110 car. And I mean, I have to say, we are all excited about seeing RL on the real race. We'll see if this will happen. Now, one of the next steps that really helped us a lot, also in the let's say, into focusing on what were the problems and how to find the bottlenecks, is really to maximize your baselines and maximize your racing baseline specifically in this case. Very simply put, when you see RLPP, the first decent reinforcement learning agent we had on the car, we saw, yes, this agent can drive decently, but really is limited a lot by sim to real. Therefore, we really pushed for driving on the real car. Similarly, with pure pursuit, we saw, yes, pure pursuit is limited in its assumptions. Let's try to embed a little bit of model into the pure pursuit, and that's how MAP came to life. So really try to maximize your baselines, because when you really see where you're losing performance, and this you can see specifically when you really try to plot and visualize everything that can be useful even remotely, you will see where are the low-hanging fruits and how you can improve your algorithms. Then another kind of trick that was very nice is to automatize the processes. The safety filter, as before, we already discussed, thanks to the great questions, is all automated. The safety filter deactivates the reinforcement learning agent. The episode is stopped. Control is returned to the main agent, which is the baseline in this case, for a preset amount of time in this case, and everything is therefore automated. Whoever is driving the experiment just needs to keep pressed basically the safety button for, well, in this case that's quite a long time, but still safety first, and then the whole RL process is automated, because I mean we're talking about long wall times. It's half an hour more or less for every episode, plus battery reset. We still don't have battery reset for now, but maybe we will have in the future, but that's still not automatized. Now, another way of automating the processes is really simplify and make everything as smooth as possible. Right now, in terms of launch files, what is really nice is that our baseline MAP can be tuned with the on-track system identification with basically one single command. You launch the base system so you can drive your car on a map. You launch your controller. This is a single command. You launch the system identification, and this is just a single launch that you can just launch, and then the car can drive, and everything is smoothly put. And making this type of procedures, after, of course, the procedure is done, you can relaunch the controller and everything is reloaded. Making this type of procedure standardized can be very helpful, especially when you're at a race day, and at the race day you cannot you have to follow this procedure maybe in the rush of the moment. Therefore, this is again a bit of an advertisement for the race stack. What can also be useful is to write up some checklists, because sometimes you cannot automatize everything, or also automatizing has a bit of a overhead at the beginning, right? It's quite hard sometimes. And for your project, maybe it can be just much easier to just do the thing by hand, but really automating the checklist so that you can rerun every step one at a time all together. And this really is for these processes that can be automatized, because sometimes to tune your car, tuning your car can be really hard. But this makes for the actual last segue into today's ForzaETH research, which is, what about if you could automatize some processes with large language models? And I've also added a little bit this part because I've seen some of the projects are in this direction. And here I will be presenting this work. This is actually work on which I haven't personally worked, but it's still from the ForzaETH group. It's from Nicholas. Many of you also might have seen him at the races. And this started as with the project Embodied AI LLM on car, enhancing autonomous driving systems with on-board deployed large language models, which is currently also an accepted paper at RSS. What this embodied AI system does is that it creates an interface between a human that can, at this point, give human commands to a robot, and then a modular structure can automatically tune, and then in a closed loop, basically reiterate the tuning on the F110 car in this specific example. We see we have a decision LLM that decides if the robot is behaving the same way as the human wants. In this simplified case, I want you to drive smoothly. Then if the robot is behaving as the human wants, the car can continue. This simple exit loop is very easy, very computational light. But then if not, you might want to reduce the lateral acceleration. And then you have a second LLM that is tasked with tuning the underlying controller, which in this case is an MPC. Now, you might say, on one side, you might say, well, why do you need two different LLMs? And this is actually a good question, but from one perspective, having the two modules separate can be computationally a little bit more effective. Indeed, the two modules were in the end also deployed on the real car. But on the other side, you can also say, yes, LLMs technically have a lot of potential, and they could, a single LLM could do the whole job. And this is, again, another work in progress, which is LLM X Robot X R1, which is this strategy, which very, very, very simply put, it is a strategy of DeepSeek R1, the big paper that collapsed NVIDIA, but it consists of putting the LLM into an RL loop. And while in the DeepSeek case, the data set was very fixed and therefore kind of static, in this case, what Nick is trying to do with another work that is still under review is to fine-tune LLMs in this case that entirely fit on the car to do the whole job onto the real car, and basically achieve what already from DeepSeek, I mean, what the R stands in R1, and with that, I mean, reasoning. Yes, with that, I will go into the fifth point, or this is the reason why I put N, main takeaway message. The takeaway message is that there's always other sources. This is just a nice way to say this is the reference page. These are mostly of the sources from the previous slides, and there are also other two specific videos that inspired part of what is in the slides and in the whole work. I will make the slides available after the meeting, and after that, I want to thank everybody. I mean, everybody from the team. I think I can actually go personally. Jonathan Becker from the work on MAP, Onur for the work on OnTrack ID, the other Jonathan Wang for RLPP, Benedict for the great work on, well, many things at this point, Andrea Carol for all the supervision, Diego for the safety filter, Joel for the, well, in this specific type for the plot, Luca for many things again, but specifically for the plots on the learning, Pavi, Liam for the work on, for the final work on LLM, and Nick also for, well, basically everything. With this, I close the talk. I think I might be a little bit over time, but any question?
This was great, Eduardo. Thank you so much. I think your team has done so much great work. And for those online and in here, we'll share this recording and also the slides as Eduardo mentioned. Oh,